Hello everyone. In this video, we're going to be evaluating an infinite sum with factorials. We have 1 plus 2 squared over 3 factorial plus 3 squared over 3 factorial plus 4 squared over 4 factorial and so on and so forth. Hopefully you get the idea. We have perfect squares in the numerator and factorials in the denominator. We can also express this using sigma notation, which I'm going to show you in a little bit, and I'll be presenting two methods. Let's go ahead and start with the first method. For my first method, obviously for both methods, I'm going to use the sigma. Let's go ahead and write this using sigma notation, which is very helpful in these cases. So my first term, notice that even though it's not explicitly stated, it is 1 squared divided by 1 factorial, because both of these numbers are 1. So it doesn't really matter whether you write it or not. So n starts with 1, goes to infinity, and we have n squared divided by n factorial. Okay? Later on, I'm planning to do the cubic version of this, which is going to be kind of similar to this. So, to be able to solve this problem, we're going to go ahead and simplify it. We're going to split it up into pieces and so on and so forth. So first of all, notice that we can write the n squared as n times n and the n factorial as n times n minus 1 factorial, because we can expand a factorial. This is 1 to infinity. Notice that the n cancels out and we end up with the following term. So what's really interesting about this sum now is that we can go ahead and split it up. But how do we split it up? That's a good question, right? We can go ahead and split it up if we kind of manipulate the numerator. Notice that the numerator is 1 more than n minus 1, which is in the denominator. So we can now do the following trick, which is commonly used, by the way. N minus 1 plus 1, we're going to go ahead and subtract 1 and add 1, which is essentially nothing, but it's going to help us split it up. So it's still going to be 1 to infinity. Now we're going to go ahead and split this into two pieces, because if you have the sigma of two sums, then you can write it as sum of two sigmas. So n equals 1 to infinity. We have n minus 1 over n minus 1 factorial plus 1 over n minus 1 factorial. And in both cases, n is 1 to infinity, because that index doesn't change, right? One thing that matters, though, if you look at the first sum, when you replace n with 1 here, you get a 0. Not at the bottom, just the numerator, right? Not the denominator, because 0 factorial is 1. Did you know that? It's not 0. 0 factorial is 1. Why is that? Because you have nothing to arrange, so there's only one way to do it. You don't arrange it, right? Easy. Counting, basically. So anyways, how do we manipulate this then? If n equals 1 gives us 0, you can start at 2, because the first term disappears anyway. So we might as well just turn this into 2 to infinity of this. And the reason behind that is because I want to go ahead and factor this. And if n equals 1, then n minus 2 factorial is going to be meaningless, because that will be negative 1 factorial. Uh-oh, that's a no-no. You don't want to go into that territory, right? So that's why we had to change the index. That's a little trick again. This is what we get as a result. And then you just need to add n equals 1 to infinity of 1 over n minus 1 factorial. Notice that we have the 1 over something factorial in both cases. The indices are different, but what's inside, the arguments are also different. But guess what? They're basically the same thing. Why? Because if n is 0, you get 1 over 0 factorial, which is 1. If n is equal to 3, you get 1 again. And then if n is equal to 4, you get 1 over 2 factorial, and then 1 over 3 factorial, so on and so forth. And you get the same thing here. So we might as well just multiply this whole thing by 2. Okay, but what is the sum? Okay, so let's talk about e to the power x. This is a good time, right? E to the power x can be defined as an infinite series, which I can write as the following. N equals 0 to infinity, x to the power n divided by n factorial. In other words, it's 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, and so on and so forth, right? Now, if you replace x with 1 on both sides, then you get e equals 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus dot, dot, dot. By the way, you can write this as 1 over 1 factorial, and this one is 1 over 0 factorial if you want. That's not super important, but that's what it is. Make sense? So this sum is E. Wow, Euler's number. Thanks to Euler. He gave us a number that we can use. So now this becomes 2E. 2E or not 2E. That didn't work. But anyways, that's the answer. Make sense? Okay. So in other words, to conclude, the first method, don't disappear because we still have the second method. N equals 0 to infinity of n squared over n factorial is 2E. All right. Let's go ahead and take a look at the second method because I think you're going to find the second method very, very different. So here's how the second method works. We're going to start with our sum again, and we need to prove or just find 2E at the end. Otherwise, one of the methods will be incorrect, right? So again, one more time, we have e to the x equals n equals 0 to infinity, x to the n divided by n factorial. Something that you should memorize, right? Now, I'm going to go ahead and do the following. I'll take this to another level. And remember, I do need an n squared. How do you get an n squared? That's a good question, right? So you can get an n squared by differentiating. Why? Because if you have something like e to the power 2x, and when you differentiate it, you get a 2 from this. And if you do that again, you get 2 squared if you differentiate this one more time, and or this double, right? You get the idea? So to get an n squared, we're going to do the following. We're going to replace x with e to the power x, which is kind of weird, right? And that's going to give us e to the power x. And everywhere you need to replace x with e to the power x. There's only one place, by the way, so no big deal. N is unchanged because we're only dealing with x. Make sense? N is the variable, but x is also kind of like a variable. All right? So now this gives us something interesting. This gives us n equals 0 to infinity, e to the power nx divided by n factorial. Guess what? We're going to differentiate e to the power nx. When you differentiate e to the nx once, you get n times e to the nx. And if you differentiate this one more time, which is differentiating this twice, you're going to get n times n times n, n times n times e to the nx, which is n squared times e to the nx. So this gives us an opportunity to get n squared in our equation, which needs to be in the numerator, by the way. That's why we're going to do the following. But what does that entail? Replacing x with e to the power x gives you this, e to the power x. So here's what we have. We have e to the power x. Let me write it one more time so you know what we're going to do next. 0 to infinity, e to the nx divided by n factorial. So here's what I need to do. Differentiate both sides. When you do, of course, you're going to differentiate term by term, but if you just differentiate the general terms, since they're going to be added with respect to x, then you should be good, right? To differentiate this, I'm going to write the same thing, multiply by the derivative of the inside, which is chain rule, which is e to the x, because the derivative of e to the x is e to the x, right? And then the right-hand side is just going to be n equals 0 to infinity, right? N e to the nx divided by n factorial. You could write this n equals 1 through, but it doesn't matter because n equals 0 is going to give us 0 anyways, but no, that's no big deal. Okay? Make sense? Guess what? We're going to differentiate one more time to get n squared. Differentiate and differentiate. Now, when you differentiate, you got to be careful. This is the product rule. The derivative of the first function, as you know, it's the same one, times the second function, plus the derivative of e to the x times the first function, which is e to the x. Cool, right? You like that? Differentiation is fun. And on the right-hand side, when you differentiate this, you get n times e to the nx, so that becomes n squared e to the nx divided by n factorial. N factorial is just a constant, so it doesn't really change, and we get the following. Super duper nice. Guess what we're going to do? We're going to replace x with 0, not with 1. Of course not. X equals 0 is going to give us what we need, because if you replace x with 0, you get n squared e to the power 0 divided by n factorial. That's exactly what we need because e to the power 0 is 1. Does that make sense? So when you replace x with 0, it's going to be e to the power 0 times e to the power 0, but it's squared. And then this one is e to the 0 times e to the 0. What is that? E to the 0 is 1. So this is going to be e times 1, because this is 1. This is 1. This is e. So e plus e equals 2e, or not 2e. Remember that. N equals 0 to infinity, n squared over n factorial. So this infamous or famous sum that we were trying to evaluate is exactly 2e, and that brings us to the same value. And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.